This is our A2Pure maths, and we're taking a look then at section 4, which is integration, and it's the first wee bit just on standard integrals. And for the first wee section, we're just going to be considering integration as the reverse process of differentiation. So you should be reasonably familiar with some of these. We know that if you differentiate sine, you get cos. That means if you integrate cos, you're going to get sine. We know that there's a wee mistake there actually, if you differentiate cos, you get minus sine. That means if you integrate sine, you would end up then with minus cos. And if you differentiate tan, you get sec squared. So if we integrate sec squared, then we're going to get tan, and different variations then of it. So we want to consider a similar differentiation that we know is going to give us the right answer. So I'm just going to go off the notes here for just a wee second just to try and explain this. Say for example we had to integrate sine 5x dx. We would try and work out what a backwards differentiation of that would be, and so we would maybe consider d by dx, because I know if I differentiate cos I get minus sine, so it's going to be something close to that. So if I differentiate cos 5x, I now know that that's going to give me minus 5 sine 5x. That means then, can we make it into this format here? So if I differentiate minus a fifth cos 5x, so what have I done from here to here? I've divided by minus 5 effectively, or multiplied by minus a fifth. Then that should give me 5 sine 5x. So if I differentiate this, I get this. So in this case, if I integrate this, I'm going to get minus a fifth cos 5x, and that's generally how this works. What you have in terms of your notes here for the first page is just lots of general examples that instead of the 5 we have an a in there, and incidentally if it's sine, 5x plus 6, the 6 has no effect really on this, it would still be minus a fifth cos 5x plus 6, but that's what it works through there in this page. And you can see then where it's come from. So we got down to here. If I differentiate sine x plus a, I get cos x plus a, so the integral is going to be the same. If I differentiate sine ax plus b, which is a bit like our sine 5x one we did a wee minute ago, we get that in just kind of different formats of that, just getting used to it. Let's take a look at a couple of wee examples. Again, we're just going to consider various things that we know. So we have cosec squared and we're integrating it. I guess if you look up your formula book, that you will see that if you differentiate cot, you get cosec squared. So we're going to try and consider then a suitable derivative. So let's actually write that. So consider, sorry, takes a while. So I'm going to look at d by dx of cot 5x over 2. If I differentiate that, what am I going to get? If you look up your formula book, at cot x differentiates to minus cosec squared, which is quite like what we have here. And then we would obviously multiply. Then sometimes you might want to use a chain rule here, and we'd let u equal 5x over 2. You end up multiplying, but effectively it's going to be minus 5 over 2 cosec squared 5x over 2. That means if I integrate minus 5 over 2, sorry, I'll put that in there, cosec squared 5x over 2 with respect to x, I would get cot 5x over 2 plus c. So we're quite close here. Let's see what I've done. So I've considered a suitable derivative. Looking at this, I know I differentiate cot, I get cosec squared. So if I differentiate this, I end up with this. So I've just written the exact opposite here. If I integrate this, I'm going to end up with this. This is quite close to what we want here. So we can do just a little bit of manipulation. Therefore, cosec squared 5x over 2 dx. We need to then, I guess, divide by the minus 5 over 2, so it's going to be the same as multiplying by minus 2/5. So it's minus 2/5 cot 5x over 2 plus c. So if we're considering then a suitable derivative, is how we work it out. Let's look at example 2. 4 cosec x cot x. Again, it looks very complicated, but in this case it's not, because we know, again, look at your formula book, that if you differentiate cosec x, you get cosec x cot x, or minus cosec x cot x. So let's consider that, and then consider how we're going to work this out. So consider d by dx of cosec x. So if we differentiate cosec x, we get minus cosec x cot x. So we just effectively need to make this 4 times bigger and change it into a negative. So therefore the integral of 4 cosec x cot x with respect to x equals minus 4 cosec x plus c.